Okay, so welcome everybody to. Okay, welcome back everybody for the final talk of the conference, for which we're very happy to have Masaki Shiegemori from Nagoya and Kyoto, who will tell us about exact non-abelian supertubes.
Okay, thank you very much for the introduction, and thank you very much for the invitation. And I feel honored to be the last speaker of this wonderful conference. So I will talk about exact non-abelian supertubes, and some of you have heard of some similar talk, similar title in Kyoto some years ago. And back then, it was not exact. This time, it's exact. So that's the point of this thing. Oh yeah, I go forward. But this one. Where does it not work? Oh. Ah. Okay, but this is in the way. Yes. Is this the second slide? I skipped some slides. Yes. Introduction. Yeah. Okay. Black hole microstates. So maybe I can be quick here. So we know that black holes have entropy, and the question is where these microstates are. That should be there because of the entropy. And we know this fusible conjecture, which is about these microstates being horizon-scaled string quantum gravity object, and black hole microstate geometry program is about, well, according to my understanding, it's about constructing microstates at smooth horizonless geometries, horizonless solutions of supergravity. And there are some setups constructing microstate geometries, and multi-center solutions are one of them. So it's a paradigm for black hole microstate geometry program, and these are solutions of 5D or 4D supergravity, and you can get them by compactifying M or 2A on Calabi-Yau, and it's going to be just T6 in this talk. And general characterization is that you can specify the solution by some harmonic functions in R3. So R3 harmonic functions are just some constant plus 1 over R singularities. So you can have multiple singularities at A1, A2, and so on. And you can have some coefficients here. And this kind of singularity or pole or center, they describe some brane sources in R3. So this gamma p describes d brane charges, and ap, they are the positions of the charges. Yeah, and okay, this solution describes multi-center configurations of branes. Okay, and there has been massive work on constructing microstate geometries using multi-center solutions, but not enough have been discovered to reproduce the black hole entropy. Most probably clearly shown by Jan de Boer, El Schoch, Mesama, Van Bleken in 2009. So to go beyond this, there are possible options. First, you have to probably consider stringy stuff because, well, fuzzballs are probably in general stringy. And maybe the second option is to go to higher dimensions, and that's probably what superstrata are about, and maybe supermaze. I don't exactly know what. Maybe I should have put hyperstratum here. I guess supermaze is the unback reacted configuration.
Yes.
Okay, so.
Without just the point in R4, so perfect spherical symmetry.
Yeah. Okay. So hyperstratum. Okay, so that's probably that should be here. Okay, but there's some other option to consider lower codimension, because in the harmonic function only consider point-like objects, but we could consider, well, extended objects. So that's also possible. So well, if there are if some things are possible, we have to look into that, and that's what this talk is about. Yes. 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 Yes.
Yeah. Does little h receive the values 1 or 0? Yes.
It's just some constant at the infinity.
Which can take any value?
Yeah, it can be
Okay,
0
okay, thank you.
if you like. Yeah.
Changes the dimension, non-compact dimensions.
Yep. Okay, so let's look at multi-center solutions with codimension 2. So you can have this harmonic function can have codimension 2 singularities, and that's actually not just you don't do it because you can do it. It's actually physically expected from super to transition. For example, if you have D2 wrapping some T2 and some other D2 wrapping some other T2, then so these are codimension 3 charges from the perspective of the harmonic solution. But after supertube transition, this goes into some NS5 along some curve. And the curve doesn't have to be in the internal direction. It can also be in the non-compact R3 direction. In that case, you're going to have some supertube in R3. And that means that you have to have some codimension 2 source in the harmonic function. And not just that, you also have to have monodromies for the harmonic functions, because if you have NS5, as you go around, B field is going to jump by 1, and B field is something that, B field is also in the harmonic function. That means that some harmonic function should jump by 1 as you go around. So they are not just smeared codimension 3 source. So codimension 2 things are genuinely new or different. So we have to consider, it's interesting to study those. Yeah, and so here D2, D2 are going to NS5, but it doesn't have to go to well-known brains. It can go to some more exotic brains. Oh, yes. Did I skip anything? Yes, I did. Okay, and this thing is not new. As I mentioned at the beginning, I did some work on this. And so the idea back then was to construct some solution of codimension 2 brains where you have monodromies. So if you go around 1, you get some monodromy represented by some matrix U1, and you have another brain with U2. And when U1 and U2 don't commute, then I call this configuration non-abelian. So the goal was to construct such solution, but back then we only did it perturbatively in some approximation, and this approximation was valid when you're close to the brains. But if you are away from the brains tubes, then you get some issues like CTCs or singular sources, and that was fine in the sense that you're not trusting the solution anyway, only near. Okay, you're trusting the solution only near the brains, but in this work, I try to do it exactly. Okay, should I wait for a bit? Not to skip. I pressed this, but it doesn't change. Yes, it did skip. Strange. Yeah. Okay. Yeah. Okay. So multi-center solutions. So let me first review multi-center solutions. So first of all, what are super solutions in 4D supergravity? Okay, these harmonic functions. Sorry, multi-center solutions came out of supersymmetry analysis in 4-dimensional supergravity. So you consider type 2A on T6, which is written as part of 3 T2s. Then you end up with 4-dimensional n equals 2 supergravity with 2 vector multiplets, ignoring hypermultiplets. Or if you regard, because you have decomposed T6 into 3 T2s. Otherwise, you will get n equals 8. And in this supergravity, you can find the most general time-like class supersymmetry solution. And it's completely specified by harmonic functions in R3. And people have found these solutions. And okay, as some of you are familiar, the harmonic functions are, there are 8 harmonic functions, B, K, L, M, and they are harmonic in this sense. And the set of solutions described by this, I call multi-center solutions. And just to be clear, so you can you can write down what the 10-dimensional fields are in terms of all these harmonic functions. I have to be checking if I'm just going by one. Okay, and because you know what the general harmonic 4-dimensional 3 centers, write down the general solution. So this harmonic function is some constant plus 1 over R singularities, as I mentioned in the introduction. And this describes multi-center configuration of branes in 2A on T6. And in general, you can have multiple centers at positions A1, A3 with coefficients gamma 1, gamma 2, gamma 3. And these gammas are the charges. And this H denotes collectively 8 harmonic functions. And V describes D6 wrapping everything. K's describe D4s. L's describe D2s. M corresponds to D0. And so on. Okay, and for example, you can construct a 4-charge black hole, supersymmetric one. If you set V to be 1 plus something over R and L to be 1 plus something over R, then this means that you're introducing D6 and D2s. And this is a single center black hole solution, and you can compute the Bekenstein-Hawking entropy to be this. So that's a simple example. And one quantity that is going to play some role in this talk is the torus modulus. And in particular, let's look at the complexified Kähler modulus for T289, which is a combination of B89, the B flux through 89 directions, plus the volume of the torus, which can be written as this kind of combination of the harmonic functions. Positive imaginary part, because T289, this is for the third torus, but you can define tau 1 and tau 2 for the first and the second tori, as you wish. Okay, so these are the moduli, and this theory has some duality group, and it includes 2 factors of SL2Z. These correspond to the T-duality in 3 tori. So this SL2Z1 corresponds to the T-duality in the first torus and so on. And for example, if you consider this third SL2Z, this acts on this Kähler modulus like this. So it acts as a fractional linear transformation given this SU2Z matrix. If you have ABCD, tau goes to eta plus B over T, theta plus T. Okay, I discussed general solutions, but I will be focusing on some particular solution where I set tau 1 and tau 2 to be 1, and tau 3, I call tau, is the only variable, only modulus. This set is called SWIP solution, and that's based on that's a supersymmetry version of IWP solution, Israel Wilson Perias solution. And I don't know why they started to call the SWIP instead of SILP. It's named by Bergchef, Kalos Ortan. Anyway, so we focus on this set. this subsector, then actually you find that for example, L1 is L2, K1 is K2, and L3 is V, and M is K3. So instead of 8 harmonic functions, you only have 4 independent ones. And let's combine the independent ones V and K1 into this complex G, and K3 and L1 into this complex F1. Sorry, F. Oh, okay, sorry, this should be F. So you have 2 complex harmonic functions. And what's nice is that in this case, you are only left with SL2Z for the third torus, and this acts on FG like this. So F and G are a doublet of this, doublet for this SL2Z. And now tau is simply F over G. Yeah. And note that if you have a source, if you have 1 over R in G and F, then you're not just having some charge for some particular harmonic function, because all the harmonic functions are related. Turning on some 1 over R in one harmonic function actually turns on many sources. So we are talking about some particular combination of charges so that these first 2 tori are trivial. Okay. Yes. And in this swept solution, the 2A fields are simple. So yeah, pretty simple. For example, these first 2 tori are just trivial. And you note that we need this imaginary tau3 to be positive, which I mentioned before. Otherwise, for example, dilaton would be negative. Sorry, the exponential of dilaton would be negative, and this torus would be closed time-like curves. So you have to reimpose this. And if F and G have the form, asymptotic form, some constant plus QF over R, QG over R, then the entropy of a single center black hole with these charges are proportional to imaginary of QF QG bar, which is proportional to QG squared times imaginary part of the tau at the horizon. So basically, unless QF, QG vanish, I mean, either if one of these vanishes, then the entropy is going to vanish. But if you have both turned on, this is going to have non-vanishing entropy. Okay. Am I going too slow? Okay. So codimension 2 solutions. Although I already mentioned this, but you can also have codimension 2 singularities in your harmonic functions. Instead of just dots, you can have curves. And they are not just smeared codimension 3 source. They can have duality monodromies. So these things are genuinely different from codimension 3 ones. And there is a physical reason to consider them, namely supertube transition. For example, this is something I already mentioned, but now we are more concrete. So if you consider D2 along 4, 5 and D2 along 6, 7, this is going to go to NS5 along some curve, lambda, and 4, 5, 6, 7 direction. And this is a dipole because it's along a closed curve along x equals f of lambda. And in this case, you can show that the harmonic functions are given by this. So G is just 1 in this case, and F is gamma plus IF, where F is the harmonic function, the usual harmonic function, because you have some charge along this thing. So this is not just NS5. You have D2 brain charges sprinkled along this word volume, and that gives rise to this harmonic function. And you can, okay, so this F is like the electric potential. And this gamma is like the magnetic potential if you regard, if you think that there's some current flowing along this, curve. So this gamma is actually multi-valued. As you go around, this gamma shifts by 1. Which one? The solution has monodromy because this gamma is monodromic as you go around. Yeah, this gamma is like the magnetic potential if you have a current flowing around. Yeah.
So
Q1, Q1 is Q. Q is the charge of D1 and D both. Okay, D2 charges are said to be equal, and that's Q.
Very good.
Yeah, sorry, I forgot to. This should be Q.
Thank you.
Masaki,
Yeah.
can you please remind what is the relationship between B, the B field, and the harmonic functions?
In this case, gamma is the basically a B field. Yeah, but this F is not describing just. I mean, this F enters in various harmonic functions. So I don't exactly remember where this enters, but yes, this certainly is the B field. Yeah. Okay, so so G is 1 and F is this combination. Then as you go around, F goes to, this gamma has a monodromy. So as you go around, F goes to F plus G, namely gamma F plus 1 because G is 1, and G is just 1. So you can say that you're undergoing this monodromy, and this monodromy is known to be the correct monodromy for NS5. And you can do something else. If you have D6 and D2 along these directions, then this is known to go to something called 522. 522 is a T-dual. It's a double T-dual of NS5. You don't have to know what this really is. And in this case, G and F are given by this. And in this case, gamma changes by 1, and that means that F and G now go like this, and that means that tau goes like this. And this is also the correct monodromy for 522. So yeah, so you can have these harmonic codimension to singularities in the harmonic function. Okay, so let me explain the general idea of what we're going to do. So the goal is to construct exact codimension 2 solutions with non-commuting monodromies. So we have seen that this doublet undergoes some monodromy as you go around. And what if you have 2 such branes with different monodromies, U1 and U2, and what if they don't commute? Because commuting monodromies, I mean, codimension 2 solutions with commuting monodromies, that is easy to construct. But this is more difficult. So let's see what the strategy is. So let's consider we are going to consider multiple rings and assume that the rings are separated by length L, roughly, and the radius is R, roughly. Initially, we consider such scale. And because we consider such configuration, it's good to introduce coordinates that are suited for this purpose. And they are toroidal coordinates. You don't have to look at this. It's like this. So you have this ring, and you have this angular coordinate sigma, which is around this ring like this. And also you have some radial direction u, and u is infinite when you are at the ring, and as you go away, u goes to 1. And actually this x3 axis, z-axis is also u equals 1. So the near ring corresponds to u equals infinity, and infinity of R3 corresponds to u goes to 1. And actually sigma equals 0. Sigma is 0 along this line and this line, and it increases as you go in, and it's pi in here. And if you want to go to R3 infinity, you have to set sigma to 0. And there is also this angular variable psi along the ring, but that doesn't play any role in this talk, because we always consider some configurations uniform along psi. And okay, so we want to consider harmonic functions. So what is the Laplace equation in this coordinate system? This is known. So Laplace equation is separable in this coordinate system if you define G to be this combination times e to the ik sigma. So it's separable. So let's do this. And G of u is the non-trivial part. And if you plug this thing in, to the Laplace equation, you get this equation, and this is the Legendre equation. And if you require that the solution is regular at the 3D infinity, namely when u is 1, then the only solution is this. This is the Legendre function. There is also q, but that diverges logarithmically at u equals 1, so we throw that away. And we assumed no dependence on the angular variable along the curve, along the ring. And if you introduce that, the Legendre function becomes the associated Legendre function. But we don't do that. Okay. And one thing, this thing is important in constructing a solution. So let's consider a near limit. So if you consider approaching the ring, and also you consider the limit where the distance between the ring is much, much smaller than the radius of the ring. So L is much, much smaller than R, and D is the distance from the ring from you. So you are very close to the ring, and the rings are close to each other. In this case, the rings look infinitely long. So you are dealing with infinite straight branes in 2 dimensions. And now Fg, the SL to Z doublet, is going to be just a function of Z. So what you are talking about is this SL to Z doublet Fz, Gz with non-trivial monodromies in this limit. So what you have to do is to find a pair of holomorphic functions Fz, Gz on this Z plane, so that the quantity, this ratio F over G has this positive imaginary part, and this also has to have non-trivial SL to Z monodromy around some singular points on the Z plane. So you have some branes, and as you go around, you have some non-trivial monodromy. And okay, this is a familiar problem. This can be solved by considering torus vibration, as was done by Seiberg and Witten in their supersymmetric gauge theory, or maybe in F theory. So we are going to discuss that soon. So the strategy is the following. So in the near limit, the problem reduces to a 2D problem of F theory, of looking at some torus vibration. And if you have some F theory solution, what you have to do is to find a full 3D solution, Fg, that reduces to the 2D solution in the near limit to some F near G near. So F near G near is the F theory solution, and some 3D solution that reduces to very close to the rings. Which infinity? 3D infinity. It's regular. Yeah. So even on the Z plane, I'm assuming that F and G are going to 0 at the infinity, and that continues to. So the harmonic functions just continues to vanish as you go to the 3D infinity. Yeah.
You said that you want to find a solution where the monodromies between the sources, as you go around the sources, do not commute.
Yes.
Can you give us some simple physical picture for what are the conditions on the sources for this to happen?
Physical condition for the sources.
When does it happen that the monodromies do not commute?
When they are
in some simple
when they are 7 branes. It is known that there are such things in string theory. And I'm going to get to that soon. Yes. Okay. So that's the question, and there's no time, so I will just give you the answer. So let's say that you have some F theory solution, namely you have some function F and G defined on the Z plane, which have some non-trivial monodromy. And as I said, you assume that they are going to decay at infinity. So you can expand your near solution in 1 over Z like this. and this z hat is defined as z over L. L is determining the scale near the in the near region, and this L can actually be complex. Okay, but anyway, you just expand. You have this expansion. Then it turns out that the full 3D solution is given by this formula. Okay, this is done by something called the matching technique, and it was discussed in my previous paper in some detail, but it was not worked out fully like this. So this is the solution. So it's complicated. And here I define this capital Z to be this combination. So this is big. So capital R is the radius, and L is the distance between the rings. So this is big. Okay, so this is a solution. And oh, why doesn't it move? So you have this Legendre polynomial. Legendre function, and this k doesn't have to be integers. They can be just fractional numbers. So dealing with pk with fractional k is a bit of a pain. So you can use what is called the Schläfli integral representation, where you represent it as some integral on the t-plane, and you have some cuts, but you avoid cuts so that you go around some cut between I1 and U, then this is well defined for any k. U is larger than 1. U is 1 at infinity and infinity near the ring. Physically, it's always larger than 1. Okay, so then the formula can be written like this, using that Schläfli representation. And okay, so that's that. And you have this annoying combination, and you can actually rewrite this in terms of some integral. This is actually related to the beta function, not the renormalization beta function, the beta function in math. And you can rewrite it like this. Anyway, and okay, so this is a correct formula for finite L and finite R. And you can easily show that this does reduce to the near region solution if you take the near limit. Yeah, that's the third line. And also, I required that my expansion only involves P, the Legendre function of the first kind, not the second kind. And this means that this function G actually does not have any constant term. So this is a harmonic function. So it can have a constant term in principle, but it doesn't. Maybe there's a way to introduce Q, and maybe we should do that, but at this point, I don't do that. Okay, and here, yeah.
Do something to the asymptotics that's undesirable?
So this is going to be always asymptotically ADS2.
Okay.
Yeah. Yes. I don't know if this is a feature or yeah, about yes. I'm not sure yet. Okay, and one thing is that imaginary tau should be always, this should be always positive, and it was guaranteed in the near region because we were using, in the near region you're using this F theory, which is based on the torus vibration. This imaginary tau being positive is guaranteed, but in this formula it's not guaranteed. Okay, so what we're going to do in the rest of the talk is to play with this by plugging in some F theory solutions.
You said I thought it would be guaranteed because you're basing this whole thing on an F theory solution. So why isn't it guaranteed?
Because I'm not based on this elliptic vibration anymore. I'm just using.
As a function of U and sigma, it's not guaranteed. As a
Sigma?
function of U and sigma, it's not
Right,
guaranteed.
right. It's not guaranteed. Yeah, very near the tubes. Yes, it is guaranteed. But if you go away, you don't know. I'm just finding some harmonic function that reduces to the F theory harmonic function. Okay, so let's play with some explicit solutions. So F theory. So let's discuss F theory very briefly. So So what's F-theory? F-theory is about having NPQ7 branes on a Z-plane. Okay, so we have 7 branes. So we have the Z-plane, and you put 7 branes. And there are not just D7 branes, but there are something called PQ7 branes. And around a PQ7 brane, you have some SL2Z monodromy for tau of Z. Here, tau of Z is the complex parameter, complex structure for some imaginary T2 in the original context of F-theory. And you consider sprinkle 7 branes with some non-trivial monodromies. Okay, what you're having in mind is that on this Z-plane at every point you have some torus fibered, and you say that the tau here is the complex structure of this torus. Then imaginary tau is always positive by construction. And this T2 is real for us. T2 is real internal T2. And how they do it is to write some equation for the torus. So this is an equation for the torus. And you have some function f and g of order n/3 and order n/2. And depending on, so okay, you choose f and g, then your torus is going to change as you go around in this complex plane. And your torus is going to change, and your tau is going to change. And as you go around some particular point, your tau is going to undergo some monodromy. And what you do here is, okay, how do you find tau? There's some relation between tau and f given by this, where this j is the Klein j invariant. Okay, that's what it is. But so we have this, and what this torus. So this is the equation for the torus in the Weierstrass form. And what you have is okay, so this is describing some xy space. And if you project that down to the x space, then what you have are cuts. So you have some 2 cuts from -infinity to some point, and some point, and some point. And you have some cycles, alpha and beta, just like this one. So this is a torus, and this is a different description of the same torus. And this torus degenerates at endpoints where the branes are. You can find when the cuts collide. So if you solve this for x, you find where the branch points are, and branch points collide when this equation, this discriminant is 0. And when this happens, the torus degenerates, and that's where the branes are. And as you go around such points, you have some monodromies for the tau. Okay, if you're familiar with this, maybe this is boring. But if you're not, this may be a bit difficult. This is a very quick summary. And actually, you're going to find some conical deficit. If you have n branes, then there is going to be conical deficit of pi n/6. And this requires that the number of branes to be less than or equal to 24. Otherwise, your Z-plane is going to be screwed. Okay, and alpha beta periods. Okay, you have alpha cycle and beta cycle, and you can define some period integral along these periods. And they are not much used in the original F-theory context, but they are the harmonic functions in our context. Namely, we define tau to be f/g, and g is the integral of dx/y along the alpha A cycle, this or this, and f is the integral of this quantity along the B cycle. And these are going to go like 1/z to the n/12 as you increase z. Okay, that's the F-theory part. Sorry, this was a bit heavy for some people. Yeah, okay. So let's look at some particular solutions. So there are, so in general, this is complicated, but back then, people studied some very simple F-theory configurations where, for example, tau is just constant by these people. And so this means that there are some ways to bunch certain number of brains together so that tau is actually constant. There are 3 ways, but one way is this one. So F is taken to be some particular polynomial, and G is related to that. And if you do that, then this discriminant is of this form. And what you're doing is to bunch together brains into groups of 6. So you can have, okay, if n is 24, you can have 4 such bunches. And as you go around each of them, the monodromy is simply -1. And in the 2B language, this is an orbifold singularity where you have one O7 plane and 4 D7 brains on top of each other. Okay, so in this case, tau is constant, but not G or F. So let's take F-theory solution of this type and compute G near F near and see what the full solution away from the ring is. Okay, so for example, single bunch, n equals 4, n equals 6. So you have a plane, the Z plane, and you have just a stack n equals 6 bunch. And this is the near region. And as you go away, you have a ring. Okay, near, you have simply 1 over Z squared. And if you plug the thing into the formula, you get this. And P0 is 1. So this is the solution. Okay. So this is a multi-valued harmonic function. And yeah, so this is written in the Cartesian coordinate. And this is not the, this is really the square root in the complex function sense. So as you go around, this function it flips the sign. And there's a branch point at x1 equals to x2 equals 0, x3 equals r, which is this ring. And okay, I'm not showing the metric, but you can show that there's a conical deficit as you go around this ring. So it's an Orion, yes.
Why is there an I in the
significance? It's really this form. So this is a complex thing, and G is complex.
So the harmonic function is complex?
The harmonic function is complex, indeed.
How does everything get packaged so that the metric and everything else is real in the end of the day?
So the actual harmonic functions are the real and imaginary parts of this.
Okay.
So yeah, they are real.
Okay.
Okay, so you have some conical deficit as you go near. So I can maybe describe the situation like this. Yes.
Have something to do with the conical deficit?
Yes. 6 means pi. If you have n, the conical deficit is pi n over 6.
Okay.
Yeah.
And so when you say that it's multi-valued, the number of multi-valuedness is infinite, or is it depends on n?
It depends on n.
Okay.
Yeah.
Is it proportional to n?
Well, it's a bit complicated. If n is 6, then it's double valued. If n is 12, it's single valued.
Okay. Thank you.
Okay, and you may wonder, for example, did I skip any page? No. Okay. So you may wonder if can you have 2 such terms? If just one complex harmonic function is fine, then why don't we have 2? No, you cannot. Because if you do this, as you go around the first ring, only this term flips the sign, but not this sign. But that is not consistent with the monodromy, because the monodromy says that the entire G should flip the sign. So you cannot do this. You can only have 1. And you may wonder, okay, is it okay to okay for the harmonic function to flip the sign? Isn't the sign somehow physical? Okay, I'm not very sure now. But the thing is that all the harmonic functions, all the 8 harmonic functions flip the sign. So that may be fine. And remember that the 2A metric has the correct form. It has always the positive torus radius. So I think this is fine, but maybe because you're flipping the sign, the charge is flipping the sign. So the supersymmetry preserved is going to be different as you go around, no?
Because the mass is also flipping the sign. So when the harmonic function flips the sign, the harmonic function locally you have mass equals to charge.
Okay.
So when the harmonic function flips the sign, you really have an object which has negative charge and negative mass. And it's a bit like an orientifold. An orientifold is supersymmetric, but if you compute mass of an orientifold and of it's still it's a negative mass, negative charge object, which is very happy.
Okay, so
and it's okay to have configurations. All the bubbling solutions have negative Gibbon-Hawking charges, and they are perfectly happy.
But you cannot have a negative mass.
No, it's a negative contribution to the mass. The full mass is positive. But if you think about the harmonic function, so you cannot have a harmonic function v equals to 1 minus 1 over r sitting in the middle of nowhere, because that's a brane which has negative mass and negative charge. But if you put that v and you put some k and you put some l and you put some m on top of it, then you can have a configuration which is perfect.
Okay, but in my case, the entire harmonic function is flipping the sign.
One harmonic function, but the full solution is determined by the full combination of the harmonic function.
Yeah.
Z1, Z2. So the question is Z1, Z2, Z3, are those flipping signs? And the worst is when the Z goes through a 0. So when you have one center positive, one center negative, and you have a 0 in between. If you don't have a 0 in between, you can flip without a problem.
Okay. Yes.
Your metric depends on the modulus of this G, right?
Yes, it does.
So,
It doesn't vanish. It only the phase. Sorry, the phase changes. So the real and imaginary parts, can go to 0. Okay, maybe I should speed up. Okay, so and there's no constant term at r equals to infinity. So this is ADS2, and there's no angular momentum in that sense. And okay, and you may wonder, okay, if there's no angular momentum, how does it compete with tension? Because it's not rotating, then how can you stay there? But this is because you have orientifolds. So this is a combination of orientifolds and D-brane. So actually, there's no tension here. So it's not inconsistent. Okay, and you can consider charge. And near infinity, this harmonic function goes like this. So the charge can be read off from this coefficient, and it's proportional to c. But because this is multi-valued, you can actually deform the Gaussian surface at the infinity near the ring like this. You cannot deform the Gaussian surface into a tubular region just covering the tube, because there's going to be contribution from, okay, if you imagine this ring, then there is some soap bubble membrane in here inside, and the Gaussian surface across that thing, because some net flux is coming out from that bubble. So and you can compute the contribution to the charge coming from the ring itself and from the bubble. And so there's some charge carried by the disk inside, and this is something called Cheshire charge, if you like. And and in the previous perturbative approach, there was some unwanted source along the ZX3 surface, but now there isn't such a thing. And this is a microstate candidate because you have charges. Yeah.
So what are the monopole and dipole charges carried by this thing?
Dipole charge.
The usual story, if I look at a super tube, it's got, say 1 brane and 5 brane charge, and then it's got some KK monopole dipole charge, blah, blah, blah.
Yeah.
What's the corresponding story here?
Yeah, dipole charge. Okay, I can measure the dipole charge by the monodromy, and if I'm allowed to call that monodromy the dipole charge, that's the that's
yeah, it's like a 7
charge.
brane. It's like a 7 brane. There's a D7 and NS7, for example, locally. Stepan.
Sorry, again, I'm just a bit confused. Where the 7 branes? So I thought so. You had these monodromies of the NS5 brane and the 522 branes.
Yeah.
So do I understand correctly that now you are bringing like 6 of these branes together to make a monodromy, which is like -1?
Yes, that's true.
So there's no orientifold. I mean, there's no
what?
There's no orientifold. I mean, there is just
there is an orientifold. You can regard. Okay, we have put 6 branes together, and if you bring particular 2 together, you can regard that as an orientifold.
I mean, it's a very weird non-geometric brane.
No geometric? Non-geometric. Yeah, well, I'm using the language of
sure, okay.
7 brane.
But how can you be sure that the supergravity approximation is...
No, I'm not.
Okay.
This is a this is a microstate solution. Okay, I really don't have time, so you can let me go on. Right, it's a free parameter. It's a charge. I mean, if you fix radius, then your charge is going to be fixed because this is made of some codimension 3 charge as well. So given that charge, the size is determined. But at this point, as a solution, it's free. Can I go forward? Is it changing? No. It's not changing. Oh, yes. Yes, now. But I cannot go further. I only have 39 pages. Why is it? What? Yeah, I only have 30. This is the end. I cannot go any further. I have more slides. I have 54. Yeah, I was too slow. Is this the end? Okay, maybe I will log in to Zoom.
Yeah, try logging to Zoom. You planned this, right? Just so you could bargain for extra time at the end of the time.
Yeah. How do?
What you are bringing is an S5 brane and 522 brane and another S5, another 522 together. It's a very, I mean, it's a very weird.
So, but do we have to call that guy?
Well, let's see if Joseph, or Nick. How do we get his laptop onto the screen?
I can share.
Here?
No, I can share.
Or you can just share it on the Zoom.
Yeah.
Okay,
I'm just sharing. I'm sharing.
now this needs to get...
Oh yes.
We can put this thing.
Yeah. That's what I'm
This
asking.
is
Can we pull
the.
that out?
Let's see. And let's put it into your. Oh, it's the wrong.
No, that.
Oh, it's okay.
No. It's
We have this. USB 2. No.
USB-C.
USB-C. Yeah, there's a USB-C
I have
dongle.
HDMI. Okay.
So. Victory. Okay, figure out. It's a complicated thing with the size, so we have to come. We don't see the, I mean.
Oh, yes.
We see the
So-
wrong
Make
slide.
sure you share this screen. Onto Zoom.
Swap, yeah.
Yes.
Beautiful.
But now what's shared?
Check the Zoom.
What about the shared screen? I think I
Zoom,
You go to your slide.
I
no,
think
I
I
don't see Masaki. I mean, I don't see anything. Masaki to share something else.
I was sharing,
Zoom, right?
Share desktop too.
but I
Just you and Masaki on the Zoom though?
Masaki's on the Zoom. I see.
I am
No, it's just someone
slideshow
else like me, so that's not
set up
Well, then there's no
slideshow.
point for it.
But it's also
No.
YouTube for the depths of time.
Oh, the YouTube, okay.
Ah. Sorry, I don't want to use the. I don't want to use the presenter
No,
tool, right?
Can you share Zoom? Just go to Zoom.
where's Zoom?
Okay.
Where's the Zoom?
This is Zoom.
Desktop two.
Yes.
Oh, good. I see everything on Zoom. Perfect.
Oh, okay.
Okay.
Good.
Good. Good.
I hear you. Okay. Let's see if I hear you on Zoom. Say something.
Hello? Yes. Very good. So how many minutes do I have now?
You have about 5.
Yeah.
French file.
Okay. So, okay, I will skip many things. So I'm done with this part. So single, I can consider single bond. Okay, let me just skip all these things. 12. If you have 12, you don't have any monodromy
What
anymore.
happens if you had 4? I vaguely remember 4 was.
You can have 2 and 3. Well, I don't know. It's just complicated. You have some monodromy. So it's going to be triple valued.
Yeah, it's the G40, and that's kind of.
Yeah. Triple valued, and yeah, you have more multi-valuedness. Okay, but let me not get into this.
It's not an orientifold. It's something different, right? It's
Yeah, it's not a string theory orientifold. It's some intrinsically F theory thing.
But it's not. It exists.
It does exist. Yes.
Story, this was just some special point in a moduli space that you picked for convenience. Are there moduli here for separating the n equals 6 bunches into separate?
Yes. But I'm just doing this for simplicity.
For simplicity, yes.
Yeah, to start with. But there's no time to go further. So, okay, so let me go to some more non-trivial, non-constant tau case. So, non-constant tau example. So it's some torus of this type, and I have some torus with these cuts, and I define A and B cycles this way, and I have the harmonic functions in the near region this way. And you can see that these branch points collide when z is 0 and 1. And this means that you have 3 groups of 2 7 branes like this. And you have some monodromies as you go around. And okay, so after some computation, you can show that this is the G and F in the full R3. And now somehow you have 3 cuts, and the period integrals are around this particular cut and along this particular path. And this means that the period integrals are now on a genus 2 Riemann surface. For some reason, I don't know why this is Riemann. This is genus 2, but yeah. I had genus 1 before. I had this curve before, but now I have this thing. Now, yes, why genus 2? Not clear to me. And I don't know if this is a general phenomenon or not. And you may wonder, okay, in this case, the choice of the contour is clear, but how did you choose this contour? Well, first of all, okay, so the formula involves some infinite sum. So because of that, new cuts can appear, and that's why you have 2 cuts here. And this part is unaffected by this change, so this remains A. But the other choice is dictated by the monodromy. If you require that you still have the monodromy that you wanted, then this should be the contour. And positivity of this imaginary tau is not guaranteed because, well, for example, there's something called Riemann bilinear relation, but it doesn't guarantee that this is positive. So you have to do some numerical check, and we have checked that this is always positive. So it's somehow safe. And what else? Asymptotic behavior. So yeah, this also have some. So this has also 0 constant term in the harmonic functions. So angular momentum is 0, and this is ADS2. And why is J 0 even though we have super tubes? So you have super tubes, and you wonder, okay, individual super tubes have angular momentum. Why isn't the total angular momentum also non-vanishing? There's some cancellation mechanism. So you have super tube angular momentum, but also there's some crossing between 2 centers, right? If you have codimension 3 centers, you have this the angular momentum being proportional to this thing. So because of this contribution, the angular momentum of the individual tubes are canceled, and somehow the angular momentum is 0. So there's somehow an intrinsic mechanism for J to be 0.
Locally, there's an angular momentum, but it cancels. When you go to the ADS2 limit, and you throw it the ones, the angular momenta between different bits cancel. So
what solution is this?
The asymptotical ADS2 solutions that you have. So just take scaling solution, the superstrata, throw away all the ones, and so they're the same, exactly the same mechanism happens. That this J becomes 0.
I see. Okay, so I just conclude. Large lower codimension solutions are largely unexplored, and we managed to construct some exact solutions. And they are candidates for black hole microstates, and the angular momentum vanishes, and somehow they are ADS2. And we have to work out some examples, but that even that cybergrid, sorry, the non-constant tau solution that I just presented, that was pretty complicated. So I wonder if we can get any more example. And we have to get more physics out of this. We are still this is work in progress, so more is to come. And why do higher genus Riemann surfaces appear? I have no idea. It's interesting, but I have no idea. And general proof that imaginary tau is positive, that's missing. And these are microstates, so we want to count them, but that's also something on the list, but it's not done yet. Okay, thank you.
More questions? Go ahead, Nick.
So, just trying to get a sense of this ADS2.
Yes.
Are these things? Can these things be made asymptotically flat, or are they just asymptotic from ADS2 times S2? Or?
Okay, as long as you have monodromies, you cannot. Because if you have a constant, if you try to add a constant, it will contradict with the monodromy.
Okay, so it's ADS2 times what? It started off as a 4-dimensional space. So ADS2 times.
Well, it depends on local geometry. Yeah, S2 basically, but because you have stuff, it's not just
there's
a
no
cross.
way to get it into asymptotically flat.
No, it's not possible. Yeah, because of monodromy. If you have a constant term, you cannot have. Yeah. So there's some interesting speculation that I skipped here. So so it's possible that maybe this is possible. You can start from some asymptotically flat solution with non-zero constants in G and F. So asymptotically flat solution, but this is possible even just only if you have bunched branes into groups of 12, because there is no monodromies. Then you can start to switch off constants in G and F. Then you're now in ADS2. Then you can start moving branes away from each other, and you have monodromies. So this sounds like these monodromic solutions can only live at the bottom of an ADS2 throat. So they seem to be somehow intrinsically Higgs branch.
So did I understand you could put 12 of them down the bottom of a throat and then make it asymptotically flat, but you could have the 12 separated?
Yeah.
Oh,
Yeah. Yeah. So this somehow is reminiscent of the 12 solutions that PL constructed.
Oh, so because in those you could have put back the ones in some of them, and you could put back the ones in some others.
For n equals 2, yes. But for n equals 1, none of them can be. Yeah.
Oh, they were even equals.
Okay, more, yeah.
So this metric that you showed, this stringy cosmic string metric of Shapiro alpha.
So I can't really.
This stringy cosmic string metric, it's really a semi-flat metric, right? I mean, you're throwing away all the modes that sort of, I mean, very close to the degeneration. You're throwing away a bunch of modes.
Near the degeneration of what?
For instance, in F theory, the metric you just were using, I mean, in that metric, the torus will just degenerate to a a thin tube, but the actual degeneration is pinching a cycle. So there's a whole series of correction that tells you which cycle pinch.
Sure.
But those you are not considering.
No,
you don't have
included those. Oh, I thought those cars.
Okay, any last questions for Masaki? And if not, since I'm the chair of the last session, it falls to me to ask you all to join me in giving a very big thank you to our organizers, so Nick, and to Josef, and of course all the support staff, so Maxime, who's not here anymore, and all the IPHT support staff. Let's give a big round of applause for a very nice conference.
But this is not the end. This is not the end. We will continue the fun to the next week.
Yeah, of course. And thank you for all of you for making this. And thank you for all of you for making it nice. Because it's nice because of all of you, not because of us.
To be continued.
Okay.